dedicated to conveying value and interpreting great books from around the world. Hello, this is Sally's Book Talk. Today I'll be interpreting for you the book The Copernican Revolution, subtitled Planetary Astronomy in the Development of Western Thought. In 1543, Polish astronomer Copernicus published On the Revolutions of the Heavenly Spheres, proposing the heliocentric theory. Then, the heliocentric theory replaced the geocentric theory and took center stage in history, a process later known as the Copernican Revolution. The Copernican Revolution wasn't just a major transformation in astronomy, it sparked revolutions in physiology, physics, chemistry, and other fields, giving birth to modern science. Therefore, the crucial importance of the Copernican Revolution is self-evident. In many books, Copernicus is portrayed as a heroic figure in the scientific revolution who waged a tenacious struggle against religious forces. Some other books depict Copernicus as a coward, fearing religious persecution and only publishing on the revolutions on his deathbed. So, what kind of person was the real Copernicus in history? What kind of revolution was the Copernican Revolution? And how did the heliocentric theory come to be accepted? The book we're discussing today will answer these questions one by one. The author, Thomas Kuhn, was a renowned 20th century American historian and philosopher of science. Kuhn specialized in theoretical physics when young, earning his PhD in physics from Harvard University. However, he gradually developed deep interest in the history of science, particularly key figures like Copernicus, Galileo, and Newton from the scientific revolution era. Thus, he switched to studying the history of science, and this very book, The Copernican Revolution, became his first major work. All right, next I'll explain the book's main content through 3 questions. First, what was the geocentric theory like before Copernicus? Second, how did Copernicus write on the revolutions and propose the heliocentric theory? Third, how did the heliocentric theory gain acceptance? Okay, let's begin with the first question. What was the geocentric theory like before Copernicus? What constitutes the Earth beneath our feet and the sky above our heads? Why do the sun, moon, and stars rise in the east and set in the west? These are things many wondered about during childhood. In ancient times, people lacked sufficient astronomical knowledge. So, there are all sorts of guesses about how heaven and earth are made and how they move. For instance, ancient Chinese believed that after Pangu created the world, the sky became round and the earth square. That's the Gatian theory. Ancient Indians thought the earth was like a shield held up by 3 elephants standing on a turtle's back. Ancient Egyptians imagined the world as a long dish stretching along the Nile, with the sky like a dome roof covering the mountains around it. But the ancient Greeks, living over 2,000 years ago, had a much more advanced understanding of the cosmos than these views. They realized the land we live on is spherical, pioneering the concept of a spherical Earth. The first person to propose that the Earth is a sphere was the ancient Greek philosopher Pythagoras. He lived in the 6th century BC and noticed during a lunar eclipse that Earth's shadow on the moon has a curved edge. So he reasoned that the Earth must be a ball. Pythagoras was also a mathematician. He believed circles and spheres were the perfect shapes crafted by God for our perfect home. By the 4th century BC, Aristotle, the big name in Greek philosophy, built on Pythagoras' ideas, cementing the geocentric theory. So, what were the key elements of Aristotle's geocentric view? First, he created a 2-sphere model, Earth and the celestial sphere. He said Earth is round and sits at the center of the celestial sphere, a perfect see-through crystal ball with stars stuck on like diamonds. Think of it like a peach. Earth's the pit and the sky's the peel. Overall, the universe is a big ball. Most stars move super regularly. We call them fixed stars. Plus, there's the sun, moon, and 5 planets: Mercury, Venus, Mars, Jupiter, Saturn. even though they basically rise in the east and set in the west too. But so because they move differently from the stars, Aristotle put each on their own crystal sphere between Earth and the sky. In Aristotle's setup, the whole cosmos is like an onion, layers of crystal spheres wrapped around the center, from innermost to outermost. Earth, Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn, and the celestial sphere of fixed stars. Moreover, Aristotle distinguished between the earthly realm and celestial realm, calling them the sublunar world and superlunar world. The sublunar world is human territory, composed of four elements: earth, water, air, and fire. This world is imperfect and constantly changing, while the superlunar world belongs to the heavens, perfect and eternal celestial bodies. Starting from the moon, they perform ceaseless uniform circular motions with the celestial spheres, never changing. The universe Aristotle described seemed perfect and matched what people observed. Since people daily saw celestial bodies rise east and set west, this theory was easily accepted by ancient Greeks, though the sun, moon, and stars moved predictably, never straying off course. But the five planets, Mercury, Venus, Mars, Jupiter, Saturn, were unruly, like the Monkey King wreaking havoc in heaven. Specifically, while planets generally moved one direction, they'd sometimes stall for days or even move backward, a persistent puzzle for Greek astronomers. Then in the 2nd century AD, Greece found its Buddha to tame this Monkey King, astronomer Ptolemy. In his work, Almagest, Ptolemy used circular mathematics to propose deferent and epicycle concepts, cracking planetary motion. Simply put, deferent and epicycle were like the Monkey King's golden headband, both circles constraining motion. The deferent is the basic circular orbit around Earth. On this, planets perform their own circles called epicycles, like bees circling flowers, while simultaneously dancing their circular dance. So the bee we see doesn't move uniformly forward, but speeds up, slows down, sometimes even reversing. But Ptolemy needed many circles to solve the five planets' motions. To match a planet's actual path, one epicycle often wasn't enough, requiring epicycles on epicycles, wheels within wheels. Fortunately, this finally resolved planetary trajectories. Although this wheel within wheels method solved the planetary trajectory problem, it actually wrecked Aristotle's cosmological model. Because in Aristotle's cosmological model, each planet was embedded in a crystal sphere and moved as the sphere rotated. This meant planets could only perform a single type of circular motion as the spheres turned. Actually, Ptolemy's deferent and epicycle were essentially mathematical methods in classical astronomy for calculating planetary positions. The circles in the deferent and epicycle were mathematical constructs for theoretical calculations, totally different from Aristotle's physical cosmic model. All right, we've covered the book's first part. What was the geocentric theory like before Copernicus? Geocentrism held that the universe consists of Earth and the celestial sphere, with Earth at the center, the sphere as the outer boundary, stars embedded on it, and between them, the sun, moon, and five planets. They moved on their respective crystal spheres. The cosmological models of Aristotle and Ptolemy, that is, geocentrism, dominated Europe for over 1,000 years, until Copernicus's theory emerged in the 16th century. So now let's discuss the book's second question. How did Copernicus propose the heliocentric theory? And how does it differ from geocentrism? Before answering this, let's get to know Copernicus. Copernicus's full name was Nicolaus Copernicus. He was a doctor of theology, and his main lifelong profession was as a canon at Frombork Cathedral. Additionally, he was highly skilled in medicine, a somewhat famous miracle doctor, and later generations called him an astronomer. But for Copernicus, astronomy was just a hobby. Copernicus lived during the Renaissance and the peak of the Reformation. Compared to the Middle Ages, people's minds were becoming more active. During this period, Driven by curiosity about nature, Europeans began enthusiastically exploring the natural world. For example, when Copernicus was 19, the Italian navigator Columbus discovered the New World of America. Of course, people's interests weren't just on land, but also in the heavens. Many astronomers emerged then, and Copernicus was one. In 1473, Copernicus was born into a wealthy family in Poland. His father was a wealthy merchant who served as a councilman. Oh, his father died young, so Copernicus was raised by his uncle, a bishop. His uncle took education seriously, sending him to study theology while also learning astronomy and mathematics. This laid a solid foundation for Copernicus's subsequent astronomical research. Scholars at that time used the same method as Ptolemy, mathematical calculations with wheels within wheels to tame the five planets. As astronomical observations became more precise, the number of epicycles and deferents Ptolemy used couldn't keep up, forcing astronomers to add more circles. As an amateur astronomer, Copernicus did the same. Initially, he didn't mean to revise Aristotle and Ptolemy's geocentric theory, but rather inherited Ptolemy's planetary model, adjusting and adding epicycles to better match observations with calculations. But through long calculations and observations, Copernicus found Ptolemy's system overly complex and still not reliably matching reality. So he tried shifting the calculation center to the sun. Surprisingly, this drastically reduced complexity. Thus, he boldly began constructing a sun-centered cosmic system, and that's how the heliocentric theory was born. Actually, Copernicus wasn't the first to try placing the sun at the universe's center. Back in the 3rd century BCE, ancient Greek philosopher Aristarchus proposed heliocentrism, but Aristotle's geocentric theory was already deeply ingrained. Aristarchus's ideas got little attention, while Copernicus initially placed the sun at the center just for calculation ease, never expecting it would shatter Aristotle's cosmic center, making the sun still and Earth move. As early as 1510, at age 37, Copernicus wrote a pamphlet called Commentarialis, outlining his heliocentric ideas and swapping Earth and Sun's positions compared to Aristotle's model. The sun is at the center, with Mercury, Venus, Earth, Mars, Jupiter, Saturn orbiting outward, and the moon revolving around Earth. This order matches modern astronomy exactly. But that initial outline was just a dozen-page manuscript circulated only among Copernicus's friends. Nevertheless, the heliocentric theory caused huge waves in astronomy and gained substantial support. Many found Copernicus's system made calculating planetary positions much easier, eliminating Ptolemy's complex computations. From 1510, when Copernicus drafted the outline proposing heliocentrism, to 1543, when he published his masterwork on the revolutions, on his deathbed, over 30 years passed. Besides his official duties, Copernicus feared religious persecution and being branded a heretic, which kept On the Revolutions unfinished for so long. Copernicus lived in a conservative Catholic region and was himself a clergyman. In that era, Catholics treated heretics brutally, often burning them at the stake. Yet, Copernicus faced no persecution during his life. He was highly respected and even served as a local governor. Moreover, Catholics then saw heliocentrism merely as a hypothesis for simplifying planetary calculations. Thus, nobody labeled him a heretic. But having witnessed executions, Copernicus hesitated until his student Rheticus became key to publishing On the Revolutions. Rheticus was Austrian. In 1539, the 25-year-old came from Austria to Poland to study mathematics under Copernicus. By then, Copernicus was a 66-year-old, plagued by illness. It was Rheticus's help that finally completed On the Revolutions. Before On the Revolutions was formally published in 1540, Rheticus wrote a pamphlet called First Account. Published first, it introduced Copernicus's work, hyping his teacher's masterpiece and spreading awareness of his ideas. Not until 1543 was On the Revolutions fully published. By then, Copernicus had suffered a stroke and lost his speech. Yet before departing this world, he saw his life's work in print. On the Revolutions, also titled On the Revolutions of the Heavenly Spheres, has 6 chapters. Its structure and methods mirror Ptolemy's Almagest, using math to calculate celestial trajectories with focus on planetary motion, while retaining Aristotle's celestial spheres concept. He just placed the sun at the center, with the order from inside out being Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, in the celestial sphere of fixed stars. Like other planets, they were embedded in their own crystal spheres and moved accordingly. Thus, although Copernicus didn't intend to start a revolutionary upheaval in science, his On the Revolutions became the spark that ignited it. So, we've covered the book's second part, how Copernicus wrote On the Revolutions and proposed the heliocentric theory. As an amateur astronomer, Copernicus aimed to improve Ptolemy's system when studying celestial motions. But he accidentally found that placing the sun at the center made calculations easier with the epicycle deference system, thus proposing heliocentrism. That became the revolution in modern astronomy, marking the start of the Copernican Revolution. Although named after Copernicus, the main revolutionary process began after his death. And next, we'll discuss the book's third question, how heliocentrism replaced geocentrism and gained acceptance. The book contains a famous quote, "The significance of On the Revolutions lies not in what it says itself, but in what it made others say." Here, others refers to a series of scientists after Copernicus, including key figures like Tycho Brahe, Kepler, Galileo, and Newton. First, let's talk about Tycho Brahe, a Danish astronomer born in 1546, 3 years after Copernicus died. Thanks to his good relations with the Danish royal family, the king funded him to build an observatory on a small island called Haven, which was Europe's most advanced at the time. Tycho conducted observations there for 20 years, becoming Europe's foremost astronomer in the late 16th century. Tycho didn't believe Earth revolved around the sun. He thought Earth was stationary. However, he found Copernicus's planetary theories and calculations seemed correct. So he proposed a geo-heliocentric system. Earth is stationary, the moon and sun orbit Earth, while other planets orbit the sun. Tycho excelled at astronomical observation and was very fortunate. In 1572 and 1577, a supernova explosion and a comet passing Earth appeared in the sky, rare celestial events many people never witness in a lifetime. Oh, Tycho had the privilege of observing them in detail. Aristotle believed the celestial realm beyond the moon contained the sun, moon, stars, and 5 planets, all moving in eternally unchanging patterns. But through observation and calculation, Tycho found the supernova and comet were in the celestial realm, yet couldn't be classified as any known celestial body in the two-sphere model. Plus, they kept changing, breaking all known celestial motion rules, clearly contradicting Aristotle's idea of perfect, unchanging, heavenly movements. Meanwhile, Tycho also observed the comet's path crossing through all 5 planets' orbits. If each planet had its own crystal sphere, this crossing would be impossible. So Tycho concluded no crystal spheres existed. Planets just follow their own orbits. Though Tycho disagreed with Copernicus, his observations still pushed astronomy forward correctly. And after Tycho's death, his colleague Johannes Kepler inherited his observatory and data. Unlike Tycho, though, Kepler was a staunch Copernican from the start, believing the sun was the center and proving it with observational data. But his observations also left him baffled. For example, precise measurements showed planet speeds varied slightly around the sun, why faster sometimes slower others. After long observation and calculation, Kepler had his eureka moment. He discovered planetary orbits weren't perfect circles at all. They were elliptical. With the sun at one focus, this became Kepler's first law of planetary motion. Planets speed up near perihelion and slow down near aphelion. Earth moves fastest in January at perihelion, slowest in July at aphelion. This discovery overturned Aristotle's belief in perfect celestial circles and spheres. Meanwhile, another scientist, Galileo, dealt a heavy blow to Aristotle's ideas. Before Galileo, astronomical observations relied entirely on naked eyes. Galileo became the first to point a telescope at the sky, and what he saw was astonishing. The moon and Mars covered in bumpy, ugly craters. Thus, Aristotle's perfect celestial realm didn't exist. Moreover, he observed Saturn had its own moons, just like Earth has the moon, confirming Earth was nearly a planet like Saturn. Galileo then aimed his telescope at the Milky Way. What looked like faint smoke to naked eyes was actually countless stars at varying distances. This led Galileo to conclude stars couldn't be embedded on a celestial sphere, as Aristotle claimed, since they varied in distance. Newton ultimately secured the Copernican Revolution's victory. A century and a half after Copernicus, Newton explained why planets orbit the sun elliptically. Gravity. Through the law of universal gravitation, we can precisely calculate planetary orbits and apply it terrestrially in daily human life. For instance, why we have weight and why we fall back when jumping, all due to gravity. Newton showed celestial and terrestrial phenomena follow the same physics, despite different trajectories. Thus, scientific thinking gradually took root. From Copernicus to Tycho, Kepler, Galileo, and Newton, the Copernican Revolution seemed smooth. But in reality, scientific exploration is always winding and revolutions arduous. Scientists lived in their times. Changing millennium-old beliefs proved immensely difficult. So when heliocentrism spread in Europe, it faced public opposition. First, it defied common sensory experience. Ancient Greek geocentrism meant Earth was stationary, aligning with people's perception of immovable ground. In an era without inertia concepts, people assumed Earth's motion would feel like standing on a moving ship, perceptible and windy, yet no one felt Earth's movement or heard rushing winds, no sensation of motion at all. Martin Luther, leader of the Protestant Reformation, saw Copernicus's heliocentrism as attention-seeking sensationalism. He declared, "Whoever wishes to appear clever must disparage accepted beliefs and champion novelty." That's what he's doing. He wanted to flip astronomy upside down. And starting with Luther, the religious opposition to heliocentrism intensified, with doctrinal constraints hindering its spread. In 1600, heliocentrism supporter Giordano Bruno was burned at the stake. At Rome's Campo dei Fiori, though his execution stemmed mainly from attacking Catholicism and promoting extreme heretical views, heliocentrism was just a minor part of his advocacy. As mentioned earlier, when Copernicus first proposed heliocentrism, it drew little religious criticism. But by Bruno's time, heliocentrism had become a symbol of rebellion against religious orthodoxy. Thus, the Roman Catholic Church's ban on heliocentric promotion became understandable. Heliocentrism faced resistance not just from commoners and clergy, but even among intellectuals, seasoned university professors. Take Galileo's telescope story we just discussed. When Galileo excitedly shared telescopic discoveries, lunar craters, Saturn's moons, the Milky Way stars, professors dismissed them, insisting celestial perfection meant his telescope must be flawed. Some argued telescopes worked only for earthly objects, becoming useless when aimed skyward. The religious ideology obstructed heliocentrism from replacing geocentrism. But in Europe then, diverse social currents existed, with some ideologies objectively advancing heliocentrism's emergence and development. For instance, the influential Neoplatonism, what was it? It evolved from Plato's philosophical foundations. a philosophical movement. Peaking in the 3rd to 5th centuries AD, it persisted through the Copernican Revolution era. A core Neoplatonist concept divided the world into two poles: light and goodness and darkness and evil. Originally metaphysical evolution, these concepts weren't natural references, but over centuries light became linked to the sun, evolving into sun worship reflected in Renaissance art and literature. In the 15th century, Italian scholar Marsilio Ficino, core figure in Florence's Platonic Academy, wrote De Sole, explicitly equating the sun with light and God. Thus placing light or God at the cosmic center held inherent logic. This became Copernicus' basis for heliocentrism and a driving force for its acceptance. Truthfully, heliocentrism's triumph wasn't just scientific progress, but a prolonged, complex ideological struggle. We've now covered the book's third part, how Copernicus's heliocentrism replaced geocentrism and gained acceptance. Here we learned how post-Copernican scientists completed the revolution, proving scientific progress marches ever forward. Simultaneously, we recognize scientific advancement faces social resistance. Fundamentally shifting mindsets remains challenging. Today, our cosmic understanding has vastly surpassed Copernicus's era. We now know the sun isn't the cosmic center. The universe contains countless galaxies, far vaster than imagined. From Big Bang theory to black hole hypotheses, new cosmic theories continually emerge. Science forever advances, but we can still gain vital insights from the Copernican Revolution. Scientific advancement requires not just scientists' exploration, but each of us breaking free from rigid mindsets. Don't be shackled by dogma. Keep pace with scientific innovation. All right, that concludes our interpretation of the Copernican Revolution. Reading notes are below the audio. See you tomorrow.